Today what we're doing is gravitational fields. I'm going to talk about gravitational potential as well. There are one or two things that I want to do in today's session. I want to go over ratio questions because in the AQA course there are lots and lots of multiple choice questions, and the gravitational fields questions in the multiple choice, they lend themselves to this ratio type of question. So they come up a lot. So I want to talk about those. I want to talk about the difference between G and V, and the fact that one is a vector and the other is a scalar, and what that means in terms of working out what the potential is or what the gravitational field strength is at any particular point. So I'm going to do that. I'm going to talk about vector sums for the vector, and just sums for the potential. Remember that the scalar potential here, all of them are negative, which makes it really complicated and difficult. It just makes it harder to think about. Anything that's negative is hard to think about, like binding energy and stuff. All those things that are negative, they're hard to think about. So I'm going to talk about that. I want to talk about graphs and the relationship between V and G, areas under graph, gradients of graphs, and so that you can swap between one thing and the other thing, so that you understand what the graphs are showing you. I want to talk about the links between gravitational fields and other things. So, for example, the derivation of Kepler's law is linking circular motion with the gravitational force, weight. I mean, it's Newton's law of gravitation. Linking those two, and the escape velocity we get from linking the potential energy with kinetic energy. And I want you to recognize the pattern, because it makes it easier for you to spot it when you've got a question about this. Right, so going to start then straight away by doing some questions. So I want to pull up, I have already pulled up some questions that are about gravitational fields. This first set, I've gone right to the end. This first set is, I think this is gravitational potential. Of the these are the gravitational fields questions on my course. So I can't. It's either potential A or potential B. I can't remember which one it is. So it's one of those, right? So, and we are going to start with. I could. Shall we go for this? No, I'm not going to go for that one. I want to do a ratio question. There we go. There's a ratio question. Okay. So question number 4, and like I say, they come up a lot in these. Where's my mouth thing? There it is. They come up a lot in these gravitational fields questions, these multiple choice questions. Okay, and you can tell that that's a ratio question because it's got a ratio in it. But sometimes it's not always easy to spot them. So the clues that it's a ratio question is. The first one is that there are two situations, and the second clue is that there's not enough information. Not enough information. Okay, and here they haven't given us anything. We don't know the masses. We don't know big G, little g. We haven't got R. All we have is a link between the gravitational field strength for one compared to the other in terms of y, x and y. Okay, so there's not enough information. That's what it feels like anyway. Right, so those are the clues. And of course, if there is an actual ratio in the question, well, that's a really big clue. Okay, but you don't always get that. Right, and what you've got to do, this is the method, okay, for solving these questions. The first thing is you've got to find the equation, and sometimes it's more than one. You might have to substitute from one into another. but you have to find the right equation. The second thing you've got to do is you've got to apply the equation twice, once to situation 1 and situation 2, okay, or planet P and planet Q, or Y or X and Y or Y. It doesn't just apply to gravitational fields questions. And then the third thing you've got to do is you've got to divide one equation by the other one, and sometimes it's the other way up. You can sometimes make them equal to each other. It's just that if you divide one by the other, all of the unknowns, they all cancel, and it always works, which is one of the reasons why I like to use this method. And so what I want you to learn from this isn't really anything about gravitational fields, it's just how to use this ratio method of solving problems. But we're going to do it for question 4. Right, so the first thing we've got to do is we've got to figure out what equation we're going to use for question 4. It tells us that the radius of a planet is x times the radius of the Earth. So if we have the radius of the Earth and we multiply it by x, that is the radius of the planet. Okay, what else have we got? The surface gravitational field of the planet is y times that of the Earth. So if I call G with the subscript E, the gravitational field strength of the Earth, that is equal to the gravitational field strength for the planet. Okay, and it says which one gives the ratio of the masses. So what we've got is we've got radius, we've got gravitational field strength, and we've got to find mass. So we need an equation which has got those in. So what we're going to do is we're going to use this equation, G big M over R squared. Right, now that is directly off your data sheet. So, and that's how you figure out which one it is. You look to see what you've got. You look to see what you've got to get. It's got to have the mass in it. It's got to have G in it. It needs to have R in it. And now we've done the first of these 3 things in our method. We've found the equation that we're going to use. Now what we're going to do is we're going to apply it twice. So we're going to do G for Earth. And G for Earth is big G, that's the universal gravitational constant, which is universal, so it doesn't change, so it's just G. M is the mass of the Earth, and R is obviously the radius of the Earth, and we've got to square it. Okay, so that's it. That's what we're going to do with our equation. Or is it? No, I think I'm going to do one further thing. I'm going to rearrange it so that I've got the mass of the Earth as the subject of the equation. So I'm going to do ME is equal to, right, and I'm just going to rearrange it. So it's GERE squared over big G. Okay, so that's what I'm going to do. Right, now I'm going to apply this equation again to the planet. I've run out of room. I'll try doing it over here. Okay, so G for the planet is equal to big G again, mass for the planet over R for the planet squared. Oh, I don't need to put that in brackets, do I? Right, okay. Right, now I am now going to rearrange it. So I'm going to get M for the planet is equal to G for the planet, R for the planet squared over big G. And now I'm going to do something extra to this one, because I want to get rid of the GP and RP, and I'm going to put in these values instead. Okay, so I've run out of room at the bottom, so I'm going to put mass for the planet is equal to, now GP is Y times GE. RP is X times RE, and I've got to square it, and I'm going to divide it by G. Okay, so those are my 2 equations. So this is equation 2, and this is equation 1. And because I want the mass of the planet, on the top, I'm going to do 2 divided by 1 instead of 1 divided by 2. So I'm going to do 2 divided by 1. Now I'm making a meal of this, but I want you to be aware of how to do this. And once you've got it, you'll be able to do them all. Right, so 2. This is mass from my planet, and that is equal to G, oh dear, let's make it look like a proper G, shall we? YGE, and then XRE, all squared over big G. Right, and now I'm going to put my second equation on the bottom. Okay, so, and that is GE RE squared and then over G. Right, now what I'm going to do is I'm going to go through and cancel everything. So my GE's cancel, my RE squareds cancel, my big G cancels. Can you see that my ratio ends up being equal to, I've got YX squared. So it is YX squared is this one, B. Can you see how to do it? So I've applied it twice and then I divided one by the other, and I got my answer. Okay, so that's a ratio question. Do I need to do any more? Please pop in a chat if you want me to do another ratio question, because I'm sure we can find one. In fact, this next one is a ratio question. Should we do another one? Put yes in the chat if you want me to do another one. No if you've had enough. Yes, please. I've got at least one yes. Yes. Yes, okay. Right, we're doing another one. Right, okay. I'm going to clear all my drawings. Right, we're going to do question 2. Okay, right, I'm just going to remind you of the rules for ratio questions. We are going to find the equation. We're going to apply it twice, and then we're going to divide one by the other. 3 rules, 1, 2, 3, okay? I'm trying to write it in as short a form as I can so that you can see how little you need to write down. Okay, so let's have a little look. What equations are we going to deal with? Can you see we've got to have the weight? This is a gravitational field strength, the gravitational force equation. Okay, so, well, W is mg, isn't it? But it's also big G, big M, little m over r squared. So we could go with either of those. So, right, gravitational potential energy, okay, potential energy, EP then is the mass times by the change in gravitational potential, okay? If we start from 0, I don't know that we're going to then we are getting, right, remember that V is big G, big M over R. So can you see I've kind of got my equations, I think, maybe. So now let's have a little read of the question. It says, when at the surface of the Earth, right, draw a little picture. This is the Earth. Right, there is the surface of the Earth. When at the surface of the Earth, the satellite has a weight W. Okay, so this is the weight of the satellite. Okay, at the surface. And a gravitational potential energy of minus U. So we've got W and minus U. Perhaps I ought to get rid of the S. Let's just get rid of that S. Right, so that's at the surface. W is our weight and minus U is our gravitational potential energy. Right, it is projected into a circular orbit whose radius is twice the radius of the Earth. Well, the radius of the Earth is about there, so we're talking about an orbit kind of like that. Woo, something like that. Okay, so there is my satellite in orbit. Okay, and that distance is r, and that distance is r, okay, to the center. Right, and it says, which line A to D in the table correctly shows what happens to the weight of the satellite and its gravitational potential energy? Right, can you see that we've got r, the radius, and we want the weight form? And so I think that we need to use, well, I think that we need to use this equation for the weight, and we need to use, well, it's the change in potential. So we've got to do, yeah, can you see, we're getting the change. It's the change in potential energy. That's what we've got to do. So we've got to do the new one minus the old one, haven't we? So m delta v then is going to be our final potential energy, which is mg over r, whatever it is, minus u. That's our final. Can you see what we've got to do? Because that, it's the difference, isn't it, in the energy that we've got to get. So okay, let's work out what okay, this is much harder than the previous one. First of all, we got to do it twice, and second of all, we've got to deal with this problem with gravitational potential being negative. Okay, so I am going to, let's do the weight first. I hope that you can see that it's over r squared, which means that the 2, because it's twice as far away from the centre of the Earth, becomes 4 because you're squaring it. So it's w over 4. So it's either that one or that one. Okay, that is the weight. Okay, so but the gravitational potential energy is a little bit more difficult, right? So what we're going to do is we're going to work out what the gravitational potential energy is there, and we're going to work out what it is there in the same kind of units, and then we're going to see what fraction of u that is. So and you can see that it's either going to be u over 2 or just u. So we're going to use the potential energy equation. So I'm going to ignore this one, and we're going to do the potential energy. So let's work out what the potential energy is at the surface. And so it's not delta, well, it is delta V, it's minus 0, because our energy at infinity is 0, so we're taking away nothing. So we're going to work out what our potential is at the surface. Oh, no, it's 0 minus it, isn't it? It's all negative. Oh, so I hate the negatives. Right, let's rub this out and try this. Let's make it clear. Let's see if I can do this. Okay, so so the EP, this is at the surface, is equal to m, and then it's delta V, right? And the V at the infinity is 0. So it's going to be, it ends up being negative. It's 0 take away big G, big M over R. That's the equation, which is why it ends up being negative. So an EP at the surface, they've called it U. So can you see that U is minus mgm over r, right? Now what we've got to do is we've got to work out what EP is in orbit. Okay, so EP in orbit, okay, is going to be m and then multiply it by v in orbit, isn't it? Again, it's like is from 0. So it becomes, can you see, mg, big M, and then it's over 2r. So, and the difference, it's the change, they want the increase. Can you see, it's the change is half of u, because this is u over 2. Can you see? So the change is u over 2. So it's that one. Oh, that was not very nice. That was not very nice. Right, let's try another one, because I didn't like that. I didn't like how that worked. Let's try this one, number 7. Okay, again, it's a ratio question. I keep telling you this happens. Look, there's another one there. Okay, so it's a ratio question. Remember, we've got to find the equation. We have to apply it twice, and then we have to divide one by the other. Right, so Earth has a density of rho. So rho for Earth is rho. And a radius of r. So r for Earth is r. The gravitational field strength at the surface is G. So G for Earth is equal to G, and that is big G, big M, over r squared. Okay, and they want to know, what is the gravitational field strength at the surface of a planet of density? Right, so the density of the planet is 2 rho, and the radius of the planet is 2r. Okay, and we've got to work out what G for the planet is. That's what we've got to do. Now, we've got a problem because we've got density and not mass. So this would be our equation. This one would be our equation, except that we've got mass instead of density. So we have to introduce another equation, which is that density is mass over volume. That's volume. I'm going to write vol because we don't want to confuse it with potential. Okay, and I'm going to rearrange that. So my mass then is my density, and then the volume of a sphere is 4/3 pi r cubed. And I'm going to put that in there instead of m. So my equation becomes G is equal to big G, and then m is rho times 4/3 pi r cubed, and we've got to divide it by r squared. Okay, so and then that 2 of those cancels with 2 of those, and you end up with, our equation then becomes it's 4/3 G rho pi r. Okay, now there's our equation. So we've done step 1. The next thing we've got to do is apply it twice. I'm going to change my colour. So I'm going to do it for Earth. 4/3 big G rho, because rho for Earth is rho, pi, and then r is r for, because r for Earth is r. Right, so we've done it once. We're going to do it again now for the planet. So we've got 4/3 big G is the same. Rho for the planet is 2 rho. Can you see? 2 rho. We've got a pi, and then r for the planet is 2r. Okay, and now what we've got to do is we've got to divide one equation by the other. So I do G, well, we want GP, so let's put GP on the top. So, and it's 4/3 G times 2 times rho times pi times 2 times r, and I've got to divide it by GE, which is G, which is 4/3 times G times rho times pi and times r. Okay, and now we can go through and we can cancel everything, So I can cancel my 3s, I can cancel my 4s, I can cancel my g's, I can cancel my rhos, I can cancel my pi's, I can cancel my r's, and I'm left with 4 on the top. So you can see that GP is equal to 4 little g, and my answer is that one. Okay, yay! Okay, that was a much better one. That was much easier. Right, I want you to have a go at some ratio questions. This next one's a ratio question when we've finished all of this. I don't want to spend any more time doing it. Right. So that is ratio questions. Right, now the next thing I wanted to talk to you about is the difference between gravitational field strength being a vector and potential being a scalar. And this is the difference between G versus potential, okay? This is a vector versus a scalar, okay? So, and that's the important learning thing that I want to get across. Okay, imagine then that we have, let's imagine that we've got 2 objects, right? So here is my Earth, and here is the Moon. Incidentally, they are not that far apart. They're probably, well, the Moon would be about, I don't know, 10 times further out than that. Honestly, they're a long way apart. Okay, so, but let's call it like this. Okay, now what I want to do is I want to show you how to find the gravitational field strength there. Okay, it's just a random point. It's not in the middle. It's not directly between the Earth and the Moon. It's somewhere else, okay? And the reason I want to do this is because occasionally this comes up and people get completely stuffed by it. So, so first things first, you need a ruler, okay? And so I've got myself a straight line, okay? And I'm going to make it dotted, right? And I'm going to go to the center of the Earth, and I'm going to draw a straight line through my my point that I'm interested in, okay? And I'm going to do another one, okay? And I'm going to do it from the center of the Moon, and again go straight through the point that I'm interested in. Right, now the reason I've done that is because the gravitational field strength vector due to the Earth points along the line towards the Earth, and the gravitational field strength vector due to the Moon points along the line toward the Moon. Okay, so I want you to be aware that you can literally draw the lines in and start putting the vectors in. Right, now the Earth is more massive and it's closer to the point that we're interested in. So I'm going to draw a vector that is reasonably big, and I'm going to make it nice and red, okay? So there is my gravitational field vector due to the Earth. So that is G due to the Earth. And remember that it's a vector. We don't very often put the little hat on it with the arrow, but quite often on your paper it will be drawn bolded. Not always though, okay? So it's a vector. Right, now let's change colour, and what I'm going to do is I'm going to draw an arrow. Now this is the gravitational field vector due to the Moon, okay? Right, now it's not as long because the Moon is less massive and the Moon is further away. So there is my blue arrow. Oh, I didn't want it to be dotted. Let's make it solid. Okay, and now what I'm going to do is I'm going to call that G due to the Moon, and again it's a vector. Right, now if you want to find the gravitational field strength at that point, which I'm going to call P, then it's the vector sum of the red line and the blue line. Okay, so we can you see, I can do this and I can do this. Okay, and the vector sum is the green one. And I want that line to be solid. Right, okay, so the green arrow is the vector sum. Okay, so the green arrow is GE plus GM. Okay, so that is G total. And if there was a mass at point P, that green arrow, that's the direction it would fall in. Can you see how you can work that out? Right, now, that's the vector sum. Let's do a similar thing, but for just the gravitational potential. Okay, so let's go back. Let's draw the Earth and the Moon again. And what I want to do now is I'm just going to kind of sketch in the gravitational field for each kind of thing. I want you to be aware that the gravitational potential lines. Oh dear, that wasn't what I intended to do. The gravitational potential lines, they cross the gravitational field lines at 90 degrees always. Okay, so I'm just trying to draw in. They are all supposed to cross in one place. Of course they don't. Right, so those are those. Right, and then I've got a very similar set of things going on over here. Da, da, da. Right, that'll do. Okay, so now technically I should draw more here because the gravitational field strength at the centre of the Earth is bigger than it is on the Moon, and the consequence is that the field lines will be closer together at the Earth than they would be at the Moon, and so I really need more field lines here. Right, now the next thing to say is that these field lines obviously aren't actually straight. Because they will join with the ones for the Moon. So if I now allow myself to just, kind of continue these, can you see I'm going to end up with something that looks a bit like this and something that looks a bit like this, and I have missed out the one in the middle. So let's do that, and then have this one is going to join there, and this one, can you see it's kind of going to go around here, and this one, and they really should join. But those are the field lines then, right? Well, what's that got to do with gravitational potential, right? Well, I didn't like that one. Let's get rid of that one. Let's draw it in again. Okay, something like that. If we draw in the equipotentials, I'm going to draw them in this funny purpley blue colour. Okay, so they would cross at 90 degrees, so they'd be circular, and they're not evenly spaced, so they'd be closer together near to the Earth and further away, further out, and they always cross the field lines at 90 degrees. Okay, and you wouldn't get as many near to the Moon because it's not it hasn't got as much mass. So kind of here, something like that. Right, okay, so now if you wanted to find out what the gravitational potential was at a point, say P, right, just like before, can you see that it's the sum of the gravitational potential due to the Moon plus the gravitational potential due to the Earth. So we can literally just add them. We're literally just adding them. So I can say that V total, okay, is equal to V due to the Earth plus V due to the moon, okay, which would be big G, big M due to the Earth over R, oh, there, over R E, right, and that distance, I'm going to draw it in red. That distance is RE, okay, plus big G, M for the moon over R for the moon, okay, and R for the moon is that distance. Oh, that's weird. That distance. Okay, and that's R for the moon, okay? So it's just the distance from the moon. And you literally just add them. There's no consideration of direction because it doesn't have a direction because it is a scalar. Okay, is everybody clear about that? Okay, what that means is that when you're doing it with electric fields and you've got, say, a positive charge and a negative charge, somewhere along that line, the potential is going to be 0, and it will just depend on the ratios of the charges. So you end up with, it's a bit like dividing it up. You know, when you would, entrance exams in year 7, well, year 6 going into year 7, and you remember those sums where it says, they always have names that begin with A, B, and C. So it was be Angela and Beryl and Charlie or something, and they run a tuck shop and they get, I don't know, £9.60 profit, and they split it in the ratio of 5 to 2 to 3 or something. And you have to decide how much Angela's going to get, how much Beryl's going to get, and how much Charlie's going to get, and it's that. So you use the gravitational potential or the electric potential, and you split it according to the way the charges are split. So if you've got, say, +2 this side and -3 the other, then there's a total charge of 5. So you split it into 5 equal parts, and that, can you see, you're going to end up with it 0, sort of 2/5 of the way along. So that is the difference between the scalar, where you literally just add them, and a vector, where you actually have to do a vector sum. Right, so that was the second thing, or third thing, can't remember. Right, so I'm going to move on. If you've got any questions, please pop them in the chat. Right, next one. Right, I wanted to do some graphs. There's a graph, there's a graph. Right, let's have a little look at this one. Okay, so number 4. Oh, and it allows us to do Kepler's derivation as well. We've got to derive Kepler's rule. Okay, so this is Kepler's, I think it's his second law. But anyway, this is that period is proportional to r cubed, the radial distance cubed. So I want you to recognize that we've got some heavy object in the middle and some less massive object in orbit around it. So like the sun and the earth, for example. And so this is going to have the mass big M. This is going to have the mass little m. Okay. And I want you to understand that the orbits are always considered circular. And so we can now find this relationship by making the centripetal force equal to the gravitational force, because it is the weight of little m in the gravitational field of big M that is holding it in orbit. So and we want the version of centripetal force that's got omega in it, because we want to do 2 pi over t instead of omega. So we're going to go with m r omega squared is equal to big G, big M, little m over r squared. Okay, that is a direct response to the one above. But we also have, omega is 2 pi over t. So I'm going to substitute for omega. So I end up with mr and then 2 pi over t all squared is equal to big G, big M, little m over r squared. Right, now I can cancel my little m's. I'm going to put my r's up on the left, my t squared up on the right, and let's put everything else on the right. So I've got r cubed on the left is equal to, and I've got t squared on the right, and I've got G big M over 4 pi squared. Okay, and that's my proportionality constant. So I've shown that r cubed is proportional to t squared, which is this one. Okay, that is one of the derivations that you absolutely need to be able to do. The other one is the escape velocity thing. Right, so we've done the first bit. Right, now it says that Pluto is a dwarf planet, and the mean orbital radius of Pluto around the sun is that distance. So now this is Pluto and this is the sun. Okay, and we've got the radius for Earth as well. Okay, and they want the orbital period of Pluto, and they want it in years. Okay, so now I want you to look at the way the questions are numbered. They've just made you work out that t squared is proportional to r cubed, which means that t squared over r cubed is equal to a constant, which means that we can go t for Earth squared over r for Earth cubed is equal to t for Pluto squared over r for Pluto cubed. And that's the equation we're going to use. We don't need the mass of either. We can just go straight in because we know what the mean orbital radius is of Pluto around the sun. So that is rp, and we know that the radius for the Earth is re, which is that one, and we know that the period of the Earth is one year, because this is in years. Can you see? So long as we've got the same units, because it's a ratio thing, it doesn't matter. So if we keep years, we're going to end up getting our orbital period of Pluto in years. So I can just multiply this thing by rp cubed, and we get tp squared, and we have to take the square root. Okay, so hopefully that's fairly straightforward. So that was good. I wanted to move on to the graph, so I'm going to zip on. Okay, we've got a small mass. It's released from just above the surface of Pluto. It has an acceleration of that. Assume Pluto has no atmosphere. It says calculate the mass of Pluto. Okay, so, well, we've got W is equal to mg, yeah, isn't it? Okay, so, okay. Little g is equal to big G, big MP, that's of Pluto, over r Pluto squared. It's just above the surface, so it's the same as the radius of Pluto, and they've given you the radius of Pluto. So you, and G, of course, that is MA, isn't it? Because it's yeah, it's just F equals MA. Okay, can you see that that's G for Pluto? Okay, so you're just using this is G for Pluto, so you can get the mass of Pluto. Right, moving on. Right, now this next bit is the graph which I wanted to do. Okay, so the graph shows the variation in gravitational potential with distance from the center of Pluto and above its surface. Okay, so at and above the surface. So you can see that the radius of Pluto that must be the radius of Pluto, right? Okay, it says a meteorite hits Pluto and ejects a lump of ice from the surface which travels vertically at an initial speed of that determine whether the ice can escape from Pluto. Okay, how are we going to do this? Okay, so this is where we do the escape velocity thing. Yay! Okay, so this is the other thing that I wanted to do, where the potential energy is equal to the kinetic energy. So this is kinetic energy at the surface and potential energy at infinity, right? Okay, so that works out to be the mass times the change in gravitational potential is equal to a half m little v squared. Please use big V's and little v's. Make it clear which you mean. Okay, so let's work out what delta V is going to be then. Can you see that the m's cancel? Whoop, whoop. So we end up with a half v squared. Okay. So we can work out that 1400 squared divided by 2 is going to be our change in potential. Okay. Now, can you see we've got the potential? This is at the surface. So V for the surface, and remember that it's negative, right? Can you see it's what? Minus 7.4. Oops, 7.4, but it's times 10 to the 5. And it's joules per kilogram. But so we want joules per kilogram, don't we? That could, because this is without the mass. So now, is it bigger or smaller than that? Can you see we've got to go from there to 0 in order to escape from Pluto? So what do we get? Is it bigger or not? Okay, so it's 1400. Woo, 1400, and we got to square it. We got to then divide that by 2, and I get 98 and then 4 zeros. Blah, don't like that. Let's press my engineering button. 980 times 10 to the 3. Okay, this is joules per kilogram. Right, now, is that bigger or smaller than that? Oh, I want them both in the same units. So I'm going to press my engineering button again. No, I want to go the other way. Okay, so this is 0.98 times 10 to the 6 joules per kilogram. And this, can you see, 10 to the 6 would make it 0.74 times 10 to the 6 joules per kilogram. Okay, can you see that this one is bigger than this one? Which means it would leave the surface. It would escape. Okay, let's go and check. I'm going to check which question number is this. 4. I mean, unless I've made a mistake. So question 4, and it was the last bit. Question 4. Centripetal force. Da, 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 da. Okay, so can you see it says sufficient initial speed to escape? Right, now I did it without actually working out the escape velocity, but I could work out the escape velocity. So let's work out what the escape velocity is using this equation, okay? Because I want you to be able to derive an escape velocity equation. Okay, so basically its potential energy is equal to the kinetic energy. So we end up with delta V, but it's V minus 0 because it's from 0. We're going to escape to 0. So all the potentials are all negative. So I suppose it's 0 minus and minus potential. It works out to be positive, okay? And that is a half times V escape squared. Okay, so V escape squared is equal to, can you see, 2 times big V, and if we want V escape, then it is root 2 big V. And of course, big V is equal to GM over R. So V escape ends up being root 2 big G big M over R. The R is square rooted as well, like that. Okay, so we can derive our escape velocity. Okay, I mean, you didn't have to. Can you see it's an or? Okay, right. I did everything that I wanted to do. Okay, so let's do one more question. I think we've just about got enough time to do one more question. Let's go back here. Have we got any other graph? That's interesting. Let's have a go at this one because it's another graph question. Okay, at a certain time, the positions of Earth and Venus are aligned so that the distance between them is a minimum. Okay, so if you think about, there's the Sun, Venus is there, Earth is there. It's when the Sun, Venus and Earth are all lined up, then that distance is a minimum. Okay, so it says, sketch on the graph on the axes below to show how the magnitude of gravitational field strength, G, varies with distance along the shortest straight line between their surfaces. Consider only the contributions to the field produced by Earth and Venus. Okay, so we're going to ignore the fact that the Sun is there or any other planets. Okay, mark values on the vertical axis of your graph. So this is the gravitational field strength. Right, now, if we say Earth is there and Venus is there, okay, actually G at the surface of Earth is equal to about 10, isn't it? It's 9.8. Okay, and G, so that's GE, and G at the surface of Venus is around about 0.9 of that. So it's around about 9-ish. Okay, I mean, obviously this is B of a question, so maybe we've got some information about it, but it's around about that. Okay, now, so we are going to put this one at 10 and this one at 9, okay, ish. And but how low does it go in the middle? Okay, does it actually go down to 0? And the answer is absolutely it does, because it's a vector. Okay, remember that we've got the gravitational field strength due to Earth there. That's at the surface, that's at the surface. Matching the gravitational field strength due to Venus there. And they cancel each other out completely at some point along that line. And it's going to be a little bit nearer to Venus than it is to Earth, because Venus is slightly less massive than the Earth, but not much, okay? But it absolutely is going to go down to 0, okay? And it's going to fall off as the square of the distance, because G is equal to big G, big M over R squared. So it's going to look something like that. That's what it's going to look like. Can you see where we get that from? Okay, so I'm just going to go and check. Let's have a little look at the graph in the answers. It's number 11. Number 11, 4, 5, 6, 7, 8, 9, 10, 11. There we go. And you can see that we've got 9.81 on the Earth bit, and 8.87. I told you it's about 0.9 that of Earth. Is the thing for, and can you see that it's slightly to the right of the central position, and it's got an 1 over r squared shape. Yay! Okay, cool. If anybody's got any questions, can you pop them in the chat now? Otherwise, I think that is it for today. I'm going to pause my